Continuing on with our 5.6 lesson, we are talking about operations with radicals. Specifically for these examples, we're looking at multiplying radicals. Now, in our first one, we want to recognize that we have three different numbers being multiplied together. We have our 5, the cubic root of 100a squared, and the cubic root of 10a. Now, because our second two numbers here both have the same index of 3, we can multiply them together and combine their radicands by multiplying. So we'll maintain our cubic root. 100 times 10 becomes 1,000. A squared times a becomes a cubed. Now from here we can recognize that 1,000 is the same as 10 cubed, and we still have our a cubed. So since we have two cubes and a cubic root, they essentially simplify each other out, and we're left with 10a. We still need to multiply that 5 out in front, and so in the end, 5 times 10a becomes 50a, and that is our final answer. Looking at our second example here, we have square root of 2ab squared times the square root of 6a cubed b squared. Now again, in this one, we have similar indices, or the same index of 2 on these. So we can multiply them together, maintaining the same index of 2, and just multiplying their radicands together. So 2 times 6 is 12. A times a cubed is a to the 4th. And b squared times b squared is b to the 4th. Now here, we recognize that we don't necessarily have perfect squares. Our 12 does not come down to a perfect square number. But we can break it down into numbers that do work out a little better. 12 is the same as 4 times 3, which is useful because we know that 4 is a perfect square. And we still need to multiply by our a to the 4th and b to the 4th. From here we recognize the square root of 4 is 2. The square root of a to the 4th, again we can recognize that as a squared squared, and we're taking the square root of it. So it comes down to just a squared, or we can recognize it as a to the 4th over 2, in which case we still have a squared. So square root of a to the 4th is a squared. Similarly, square root of b to the 4th is b squared. And we can't forget our square root of 3 here. That doesn't simplify at all anymore. So we're just left with the square root of 3. And this is our final answer in its simplest form. When we add and subtract radicals, again remembering to simplify them, in this case it would be like saying we have a 3x minus 5y plus 4z. Because our radicals that we're looking at, even though they have the same index, they don't have the same radicand. So we can't necessarily combine them quite yet. We need to get them in a form where they are combinable, in which case we need both the same index and the same radicand. So to do that, we can change all of our numbers into simpler forms. So our first one here, 3 square roots of 45, we can simplify that down to 3 times square root of 9 square root of 5, because 9 times 5 is 45. We also recognize that the square root of 9 is 3, so we have 3 times 3 times the square root of 5. And when we simplify that down, 3 times 3 is 9 square roots of 5. Looking at our second number, we have negative 5 square roots of 80. This one may not be as obvious to see right away, but we know that we're going to be using the negative 5 stays there. We want a square root of 5 so that we can combine it, and 5 times 16 is what gets us to 80. So now that we have it in a form with a root 5, we can notice that our root 16 is a perfect square, and that leaves us with negative 5 out here still, times 4, because 4 is the square root of 16, times the square root of 5, and negative 5 times 4 is negative 20 square roots of 5. And looking at our last one, we see that we have 4 square roots of 20. 4 times, again we want a root 5, and 5 times 4 gets us to 20. 4 is a perfect square. Square root of 4 is 2. So we have 4 from before being multiplied by square root of 4 is 2. And we still have our square root of 5. 4 times 2 is 8 square roots of 5. So now at this point, we have 9 square roots of 5 minus 20 square roots of 5 plus 8 square roots of 5. Now this would be like saying 9x minus 20x plus 8x. Because our square root of 5, they have the same index and the same radicand. So they are combinable at this point. So when we carry that out, 9 minus 20 plus 8 becomes negative 3x, or in this case, it actually becomes negative 3 square roots of 5. And this then is our final answer. Moving on to our next example, we have the cubic root of 54 minus the cubic root of 16. Now neither 15 nor 16 are perfect cubes, so we want to get them into forms that are. So we can recognize that 54 is 27 times 2, and again maintaining the cubic root of each of these, and 16 is cubic root of 8 times the cubic root of 2. Now these are nice numbers because we have a cubic root of 2 in each, so we can combine them. And in both cases, 27 and 8 are perfect cubes. The cubic root of 27 becomes 3, and we can tell that from our handy-dandy table that was given. The cubic root of 8, again, handy-dandy table will tell us 2. And again, the cubic root of 2. In this case now, we combine our 3 cube roots of 2 minus 2 cube roots of 2, leaves us just with 1 cube root of 2, which we can recognize as just the cubic root of 2. So this would be our final answer. When we multiply radicals, and again, remembering to simplify them as much as possible, we recognize that we are using binomials in these cases. And if we remember back to early problems, anytime we multiply binomials, we want to FOIL. So if we FOIL this first one, our first is going to be 2 square roots of 3 times 3, which leaves us with 6 square roots of 3. If we do our outer, 2 square roots of 3 and negative square root of 3, that negative comes along for the ride. Square root of 3 times square root of 3 becomes 3, and we can't forget the 2 there. This is going to become negative 6. When we do our inners together, 3 square roots of 5 times 3 becomes 9 square roots of 5, which is already in its simplest form. And our last ones, we look at 3 square roots of 5 and again negative square root of 3. The negative comes along, as does the 3. Square root of 5 times square root of 3 becomes square root of 15. Now in this case, none of our numbers are combinable. None of them have similar indices and similar radicands, so we can't simplify them down any further. So we're just left with 6 square roots of 3 minus 6 plus 9 square roots of 5 minus 3 square roots of 15. And that becomes our final answer. Now in some cases, this we'll notice that we end up with kind of these long numbers that are kind of messy with all the radicals being added in there. Some cases it turns out that we can get rid of some of the radicals, and in this example we'll see how that looks. Again, we have two binomials, so we want to FOIL them out. So we look at our first, outer, inner, and last. If we look at our first ones, 4 square roots of 2 times 4 square roots of 2 becomes 16 square roots of 4. Well, the square root of 4 is just 2, so it basically becomes 16 times 2, which we know is 32. If we look at our outer terms, we have 4 square roots of 2 times negative 7. Well, the negative comes along for the ride. 7 times 4 is 28, and we still have our square roots of 2. Looking at our inners, we have 7 and 4 square roots of 2. 7 times 4 is 28, and the square root of 2 is still there. And our last ones, we have 7 and a negative 7. That becomes negative 49. Now at this point, we can combine some of these. We have a negative 28 square root of 2 and a positive 28 square root of 2. Those will subtract each other out, so we don't have to look at those ones at all. So now all we have left is 32 minus 49, which we can see is negative 17. So in this case, we were left with just one constant number.